Example 17.5 part C gives us h, which is a rational function. We just studied rational functions in section 16, so we can see here that we have a polynomial divided by a polynomial, and let's start with saying y equals 2x plus 1 all divided by x minus 3. So our goal here is to eventually be able to write the inverse function for this, but I want to check to verify that it is in fact one-to-one, because if it's one-to-one, then there's really no reason to proceed with this and say that there is no inverse function that exists. And certainly with a rational function, it is possible for it to not pass the horizontal line test. That definitely is possible. So let's look at it. 2x plus 1 over x minus 3. There's a domain restriction of 3, and I'm going to graph everything about this in one color, so that way when we put the inverse on here, we'll put that in a totally separate color so we can see the difference, because this is going to get a little messy. There's a vertical asymptote located at x equals 3. There is a x-intercept at -1/2. There is a y-intercept at -1/3. And there is a horizontal asymptote at +2. So you'll notice that I'm not writing down all the steps for graphing. I've done this enough times where I can do that without having to write it all down. Certainly with section 16 being a recent topic, I would encourage you to do the steps for yourself and then graph this on your own. And again, the purpose here is not to get the most beautiful graph. The purpose of graphing here is really just to verify that it's a one-to-one function. So just generally trying to graph this, it's going to look something like this for the interval to the left of the vertical asymptote, and then for the interval to the right of the vertical asymptote, it ends up looking something kind of like this. So here we have the graph of h. And you would have to make a table to verify all this information, but it would look like this, and ultimately it does pass the horizontal line test everywhere that you try to draw a horizontal line. So it is a one-to-one function. Let's proceed with the switching of the x and y. Now this is going to present a unique issue that we did not have with either part A or part B of example 17.5, and that is when we get to switching the x and y, we have y in two different places. This does make it a little more challenging to be able to solve for y, which is what step 4 wants us to do. So the immediate concern is to try to get rid of the fraction that I'm dealing with here. I've got x is equal to this fraction, so I'm going to multiply both sides by y minus 3. That will make the y minus 3's cancel on the right, but on the left I can distribute x with y minus 3, and that's going to give me xy minus 3x is equal to 2y plus 1. And I know this doesn't fix the issue of having multiple instances of y, but it at least gets us into a position where it looks a little bit more like a polynomial, and it doesn't look like a rational function anymore. So our next step then is to collect all of the y terms on one side. Anything that doesn't involve y needs to go to the other. So I'm going to collect all of the y terms on the left. So that means I'm going to subtract 2y from both sides, and that's going to give me xy minus 2y. The 2y's will cancel on the right, leaving me with just, I still have minus 3x on the left, all equal to 1. So all the y's are on one side, but I still have a term on the left side that does not involve y. This is where I'm going to add 3x to both sides, and the 3x's will cancel on the left side, leaving me with xy minus 2y is equal to 3x plus 1. So on the left-hand side, everything involves a y. Factor that out as a common factor, and you're going to have y times x minus 2 is equal to 3x plus 1. Then you divide both sides by x minus 2, and you're going to have y equals 3x plus 1, all divided by x minus 2. So we were able to successfully get that two instances of y down to just the one instance, and then this is what we can call H inverse. H inverse of x is going to be equal to 3x plus 1 over x minus 2. So even though we took it out of the rational function look by getting rid of the fraction, once we got the y into that one instance, we had to then divide back by the x minus 2, creating the rational function again. So the inverse of this rational function is another rational function. So I want to take a look at the graph for this one, and I'm going to do this entirely in red. So for this one, we have x minus 2 in the denominator, which means we have a discontinuity at 2, and you can verify that this is going to end up being a vertical asymptote located at 2. And then the horizontal asymptote is going to end up being positive 3. The x-intercept is going to be negative 1/3. And then the y-intercept is going to be negative 1/2. So when I plot this, for the left side of the vertical asymptote, I'm going to get something that looks like this. And then for the right side of the vertical asymptote, we get something that looks kind of like this. And this is going to be called H inverse. So I wasn't being super exact here with this, but certainly if we were to try to draw the line y equals x in here, it's pretty close. And if I had taken a little more time with the top right corner of this graph, we would have gotten those two pieces to intersect right on the line. But you can see how even with these, there is that same symmetry going on between the across the line y equals x here with that reflection. So this would certainly be the most complex of the inverses that we could create, because the rational function is so far the most complicated function that we've dealt with.